Hey everyone, and welcome. So today we're going to dive into a real classic, a coding problem that you are almost guaranteed to see in a technical interview at some point.
Yep, I'm talking about companies like Google, Microsoft, Amazon, you name it. They love this question because it's a perfect test of how you handle matrix traversal, manage tricky boundaries, and of course, write some really clean and efficient code.
All right, so here's our game plan. We're going to start by making sure we get what the problem's all about. Then I'll show you this awesome peeling the matrix strategy. After that, we'll walk through the 4-step loop that makes it all work, handle those annoying edge cases, check out its performance, and then wrap it all up with the key things you absolutely have to remember. Okay, first things first. Let's make sure we are all crystal clear on what the challenge is actually asking for. So the goal here is pretty simple on the surface. You've got a grid of numbers, right? Your job is to read them all out, but not just row by row. You have to start in the top left and spiral your way inwards, kind of like you're drawing a snail shell.
Let's make this real with an example. So you see this matrix on the left? Now look at the output. It's not just a simple 1, 2, 3, 4, 5, 6. No way. You have to trace the path. We go right across the top, that's 1, 2, 3. Then we go down the right side, grabbing the 6 and the 9. Then it's left across the bottom for 8 and 7. Up the left side to get the 4. And finally, we spiral right into the middle to get that last number, 5.
Okay, so how do we actually do this? Let's get into the most efficient way to solve it. Seriously, this is the approach you're going to want to show off in an interview. And this visual just nails the core idea. Instead of getting lost trying to trace one super complex path, we're going to think in layers. It's literally like peeling an onion. We'll process that full outer boundary first, then we shrink our world and do the exact same thing on the smaller inner part.
And to keep track of these shrinking boundaries, we're going to use 4 super simple pointers. We'll have top and bottom to mark our row boundaries, and left and right for the columns. These 4 variables are all we need to define the rectangle we're working on at any given moment.
All right, now for the fun part. Let's break down the 4 key moves that make up one full peel of the matrix. This right here, this is the heart of the whole algorithm.
First, we start at the top. We move from left to right, scooping up every element in that top row and adding it to our result. Once that's done, we know we're never going to see that row again, so we just bump our top pointer down by 1. Simple.
Next up, we head down, we travel along the rightmost column, starting from our new top position all the way to the bottom. After we've grabbed all those numbers, we shrink our right boundary inward by 1. That column is done.
Okay, now we switch things up. We move from right to left across the bottom row. Once we've done that, we're finished with the bottom, so we move our bottom boundary up by 1.
And finally, to complete one full layer, we travel up the leftmost column. With that done, we shrink the left boundary inward. And just like that, we have successfully peeled one entire layer off our matrix.
So that's one full cycle. The really critical part here is that we keep repeating these 4 steps over and over inside a loop. And the big question is, when do we stop? Well, the loop keeps going as long as our boundaries haven't crossed each other. The condition you have to remember is top is less than or equal to bottom, and left is less than or equal to right.
Now, this approach is super elegant, but, and this is a big but, we've got to talk about some important edge cases that can totally trip you up in an interview. This is where you separate yourself from the pack and show you've really thought it through.
So here's a classic follow-up an interviewer might ask. What happens if the matrix isn't a nice, pretty square? What if you just get a single long row or a single tall column? If we're not careful, our simple 4-step loop could actually end up reading the same elements twice.
Oops. Luckily, the fix is actually pretty simple. We just need to add a couple of extra checks inside our loop. So, after we move across the top, we ask, hey, is there even still a valid bottom row to traverse? And after we go down the right side, we check, is there still a left column to move up? These little checks are what prevent us from accidentally double counting.
Okay, let's take a quick look at the performance of our solution and why, when you get right down to it, this is the optimal approach. So you could solve this another way, maybe by simulating the path and using a whole separate visited matrix to keep track of where you've been. But just look at this table. It tells the whole story. While they both take O of m times n time, because you have to visit every element once, our boundary traversal method is way better on space. It uses constant extra space, O of 1. That other approach, it eats up a ton of memory, O of m times n, space, which makes it far less efficient. And you know, showing you're aware of a few variations can really impress an interviewer.
What if they ask for a counterclockwise spiral? Easy. You just change the order of your 4 steps. What about a matrix with an odd dimension, like a 3x3 or 5x5? Good news, our boundary approach handles that middle element all on its own. No extra code needed. And for something really advanced, like a sparse matrix, you'd want to talk about a coordinate-based approach.
All right, let's bring it all home. We're going to wrap this up with the most important points that you need to lock into your brain before you walk into that interview.
Seriously, if you just remember these 5 things, you are golden. Number 1, use the 4-pointer boundary traversal. It's the optimal solution. 2, think in layers. Peel that onion, traverse the boundary, then shrink it. 3, burn that loop condition into your memory, while top less than equals to bottom and left less than equals to right. 4, don't forget to handle those edge cases, those single rows and columns, with the extra checks. And finally, number 5, know your complexity. O of m times n time, and that beautiful O of 1 space.
And to leave you with a little brain teaser, we've just totally mastered how to read a matrix in a spiral. But what if the problem was flipped? How would you take this exact same logic and use it to fill an empty matrix in a spiral pattern?
Hey, if this explainer really helped clear things up for you, a quick like and subscribe would be awesome. It honestly helps a ton. Thanks so much for watching, and I will see you in the next one.